then we continue. We were talking about RNN-based trackers, and we had very good examples, two examples, one from an ICPR paper and the other from a CVPR paper. Now, at this point, I'm going to jump to a different type of tracker, for a different type of signal, because trackers, I mean, the computer vision society is so large that they kind of manipulate everything, but tracking is not the problem of only the computer vision society. People have been working on tracking for, I don't know, like a century, especially the radar people, because before there was vision, there was radar. And in radar, tracking is a very sophisticated problem as well, because you have a very simple signal. And you are trying to track a target, and usually multiple targets. So this is a paper where the idea of RNN-based tracking applied to multiple targets in radar. And they simply use the BILSTM. Let me go over the paper because it will make more sense that way. Okay, in the field of radar data processing. Very nice introduction. Traditional maneuvering target tracking algorithms assume that the target movements can be modeled by predefined multiple mathematical models. Well, I don't know if it makes sense to you, but let me try to make this more sense to you guys. So in a radar, so this is a radar. Let me just draw a radar to you. This is a radar. So what a nice radar, as you can see. So it is just turning around. So it's like turning around. And there's a target. Just what a stupid target. So it's target, it's sending some waves, okay? So while it's turning, it's got this, as you can see, you remember how radars look like. So there's a dots will appear, but it will just turn around, and as it turns around, it's trying to see if there is something. So these are called detections. So each detection will have an azimuth angle, which is the angle that it's looking at, and the distance measure, because depending on this electromagnetic wave being sent and received back, it makes a calculation for the distance. And with this azimuth angle and the distance, because it's as the azimuth angle changes, there's a signal for it, because depending on how fast it changes, rotates. And there's this distance measure that is calculated from the incoming wave. So we have this observation. This is called an observation, guys. From these observations, usually in radars, they do some sort of tracking, which is actually the detection part. And as a result of this detection, what these guys have in common in radars is some candidate targets and their locations. So it is like candidate target 1 as location, let's say azimuth 1, distance 1, because it's a spherical, circular coordinate plane. Candidate 2 will have azimuth 1, distance 2. Candidate 3 will azimuth 3, distance 3. These candidates are not necessarily targets. Maybe they are noise, because there could be noise. I mean, in radar, there are a lot of noise. So these are some number of observations. We call them candidate targets. Okay, these candidates are obtained by a specific preprocessing, signal processing application on radars to detect the candidates. Now we feed them to a deep MMT to get the actual outputs. Well, the nice thing is this deep MMT entity network is deep multi-target tracking network is LSTM based, it's BILSTM based, and it has the capacity to overcome false targets, because a target will flash, and in the next incoming data, let's call it next frame, there's no flash. Well, it's a false target. The BILSTM can handle this because it has the knowledge of history. Plus, when there are multiple targets, I mean, crossing each other, it will have the capacity to differentiate the trajectories. So for example, one target was flying like this, and the other target was flying like here, okay? So at this point, they will be on top of each other. So how to differentiate them? Well, one of them was moving this, so in the next frame, the first target will be here, and the second target will be here. So depending on their initial motion, the MMT will handle that situation, right? So let me get back to the paper. What this guy says is, traditionally, this was done using mathematical models. Actually, I don't know if you've ever worked on target tracking for radars or target tracking for IRST, infrared search and track systems. These are being handled usually by traditionally PDA algorithms, probabilistic data association algorithms, PDA algorithms, joint PDA algorithms. These are some algorithms based on Kalman filter trackers. Kalman filter trackers are the actually aforementioned mathematical models for target tracking. And these models model the maneuvering, tracking targets they are maneuvering using some predefined models. So it is like if it's a linear Kalman model, it assumes that it makes a linear model. If it's an extended Kalman model, maybe it could assume that it can make, I don't know, second order movement. But these models are fixed models. So what they do is, actually, this is a very nice paper. If you're into this target tracking, it talks about these models right there. So this is the real acceleration of the target, and this is the observation. So using the observation, which is estimated by a kind of algorithm, which hybrid grid MM. The MM was what was the MM? Many multiple model algorithms. They use many models. So using a algorithm, a traditional, not deep learning model, this is a depiction of how they estimate the target movement. With deep learning trackers, we don't have to do this. This is a paper which is trying to replace those Kalman-based or model-based trackers with deep learning models. And actually, as an introductory to the subject, they provide information to these model-based trackers first. You're not interested in them. Okay, this is for example a target XY position, and these are the candidates that I talked about. We try to find the actual targets out of these candidates. Not an easy job. Okay, so you see observation, distance, so ground truth of the trajectory. So by using the observation of the azimuth and the distance, we try to get a trajectory out of it. And in these pages, they talk about how that pre-processing is handled. We are not interested in them. What we're interested in is, we have the input, we have a deep MMT, and I'll get to that deep MMT, guys. This is the pre-processing part, as you can see. Okay. The output is actually not detections only, but trajectories, because you can easily put those candidates into trajectories. Okay. These trajectories are being fed to a bidirectional LSTM layer. The LSTM layer is to decide which input trajectories are real targets and how to re-identify them. So always saying, this is target 1 from the previous frames, this is target 2 from the previous frames, this is noise. That's what it does. And they just train the BLSTM with the pre-processed data obtained here, with the actual data. And they've got very nice results, they say. Deep MMT network, observation segment, they kind of give the details of the reconstruction step. Given the observation segments, the network can generate corresponding corrected trajectory segments. The trajectories are corrected by the BLSTM, which are combined with 4 seconds overlap. I mean, they kind of feed trajectories with a 4 seconds overlap. That's how they operationalized it, because the incoming data is just continuous, and they don't want, they kind of decided to put overlapping windows, and they just talk about these overlapping windows here, and there's some results. In the end, in that space of candidate pixels, these are the multiple trajectories they obtain. Nice idea. Well, can you apply it? Well, this was the radar idea. Can we apply it to some kind of vision problem? Yes, you can. Actually, it's already being applied. For example, for multiple people tracking, because multiple people tracking is a very difficult job, guys. You remember that figure from the previous hour? So this is just multiple people tracking. They move the same. They have sort of most probably different appearance models, but it's difficult to differentiate them. So there is a very nice paper from neurocomputing, which I'm going to be talking about next. Okay, this is also multiple target. So at this point, with this hour, I jumped to multiple target trackers, not a single target tracker. In a single target tracker, the focus in the two papers from the previous hour, the focus was to learn the appearance model in a perfect manner. But in this type of problems, the appearance model is so, weak. We are trying to differentiate different targets in a multiple target environment, and we are trying to overcome some noisy targets, false targets as well. So these type of trackers are focusing on a different aspect of the problem. Okay, let's see. So the radar problem was an example. This multi-people target tracking is an implementation of the same idea into computer vision. Let's see. They present a deep learning-based approach, which has the name dual CNN RNN, for multiple people tracking. They follow tracking by detection paradigm, which is actually similar to the radar thing, because the radar did the candidate detection first, then just pruned the data, cleaned the data for multiple targets, and while doing it, at the heart of it, it included a type of LSTM. Well, this will be the same. By first training a CNN to measure the similarity of two detection boxes, and they solved this data association problem. Actually, in this literature of multiple target tracking, when you have many candidates in which you don't know which target is which and which ones are the false targets, when you associate them to actual targets and when you create a sequence of that target trajectory, this is called data association problem, where the PDA, probabilistic data association algorithm names comes from this data association title. They build a graph with nodes as detections and edge costs that are outputs of the CNN. To solve the problem, they apply a graph-based approach, which I'm going to be talking about. Very sophisticated problem. So the problems they attack is a CNN for determining the pairwise detection affinity cost. So I'm going to get there. An RNN for nonlinear motion prediction. The same thing that the radar tracker did. A tracklet stitching algorithm using motion patterns obtained by RNNs in order to handle long occlusions. They have a thing for the long occlusions, guys. Because in people tracking, you have long occlusions. For example, somebody gets behind someone and just comes up 5 seconds later. That's a long occlusion. Because 5 seconds is like, if you have a 30 frames per second video, it is like 150 frames later, long occlusion, because the dependencies at each frame. Okay, let me get to the algorithm. So as you can see, we have the video sequences. We do a detection first. Then, using a CNN, the detected squares are matched to each other. And that matching information is represented on a graph. I'm going to talk about this. So, video sequences, detections. This CNN gives a weight value to each detection. So this is frame 1 to frame n. So this guy can be this guy cannot be this guy. So these detection cues, these weights are being represented in a graph, these relations. Okay. And they do a type of optimization for the graph. This Kernighan-Lin optimizer is a optimizer for the graph to learn which edges are the actual neighbors according to a criteria. I'm going to be talking about it. So in the end, actually, what this part do is it creates a clean version of candidates list. Still not entirely correct, but it clean, cleaned, a more improved version of the candidate list, represented in a graph. And this graph will create trajectories for us. Okay, so the output of this first part is the multiple trajectories, which we don't know to be true yet. And those trajectories will be reconstructed and corrected by the RNN. Quite similar to the radar, but using different tools and different black boxes. Okay, let's see what happens in this paper. Exciting papers, huh? Detection similarity computation using a CNN, blah, blah. It's just, they also talk about where they get the video sequence. So the structure of the proposed CNN for similarity computation. It is not a Siamese network. It could have been a Siamese network because usually in CNN similarity comparison, we use Siamese networks, but they didn't do that. So what they do is they kind of use a CNN to obtain a similarity for two detections. Okay, I understand, I'm their choice. So in the end, they have this list of detections represented on a graph. I'm going to get to the graph part. So at each frame, they've got these detections. They'll have to re-identify these detections because we have got multiple detections. Which one is which? I mean, from frame 100, this one to the next frame, I need to identify this guy as this guy. And they've got this strange annotation. So I need to speed it. Okay, hold. So as you can see, they've got these values. You can see. And after re-identifying, they have some sort of these frame numbers. So this is 9 and 9. They have a similarity measure. 6 could be 6 with a similarity measure. 4 could be 4 with a similarity measure, like a percentage you may think of. And if there are errors, they correct those errors. Okay? Okay. So what they do is, let me get to that part. In this graph, this is a strange graph. Every edge is connected to another edge, which represents that detection could be a detection from the previous frame as the same person. So what I'm trying to say is the green nodes are the detections taken from a frame T1. The yellow nodes are the detections taken from T2, the frame T2. And the red ones are the detections taken from T3. As you can see, the number of detections may change from frame to frame. What it does is, it is connected to each detection from the previous frame. And the detection, these lines are actually detection cues, which means how strong the similarity is. So you have a graph with connections having some weights. And this optimizer prunes this graph, so cleans some edges, so that you create some trajectories. But these trajectories are not necessarily one only. I mean, a single node may exist in multiple trajectories. So that's why these trajectories that are fed to the RNN are some candidates list. So one node can exist in multiple trajectories. And the RNN will do its job by cleaning. So this is the RNN. As you can see, this is the RNN. So candidate 1, position 1, candidate 2, position 2, candidate 1, width 1, the box width, height 1, candidate 2, candidate 3, candidate 4, and in the end, at the output, I feed the out like a sequence modeling. This is my first object, this is my second object, this is my third object, and in the end, it says there are no objects kind of flag, and you know that there are multiple objects. This is how they handle the problem. So this is the input stage, this is the prediction stage, and this input is the clean candidate results as the output taken from here. So let me just, it's here. Very nice idea. Any questions about this paper? Paper. Good. We've covered two examples for single target trackers where the appearance model information was important, where the BILSTM, the RNN, focused on learning that information. And then two other examples where appearance model information was not the thing of the main focus, but there were multiple targets, and differentiating targets from each other was the main focus. And well, the LSTM, the RNN model, was used for this purpose. So we've seen that the LSTM, the sequence model, can be used for both of them in these problems. Now, I'm going to be talking about the next stage of events, which is the transformer-based trackers. Well, if you haven't realized it already before this lecture, I think at this point, you know that tracking is a sequence-to-sequence problem. And the best sequence-to-sequence modelers we have currently are the transformers. And the transformers, vision transformers, is a thing of like 1 year. So in this last year, people have thought about this. And when they first saw the vision transformer, well, transformers works for vision. Well, transformers are sequence-to-sequence modelers. And the problem in vision for sequence-to-sequence modeling is tracking. So why not apply it to transformers, they said. And they have been working for this entire year. And in the last CVPR, 2021, held in June, there were 2 transformer tracking papers. One of them treating the tracking problem as a sequence. The other of them is not treating the problem as a sequence. So 2 different approaches. I'm going to talk about both of them. First one, transformer tracker, CVPR 2001 by some Chinese university guys from Dalian University. I don't know where that is, of course I don't know. But I've been to China, I've been to Peking and Beijing, and they were fantastic. Okay, now the first transformer-based tracker that I'm going to show you, frankly, does not treat the problem as a sequence-to-sequence problem as transformers do. It is trying to use the attention mechanism of the transformer just like a filter for the tracker. So as you can see, if I could just make a similarity measure between the frames, just like a filter does, using the attention mechanism, that would create a tracker for me, it says. That's the approach they handle. So correlation acts as a critical role in tracking field, especially in recent popular Siamese-based trackers, and before that as well. Before deep learning or Siamese networks, correlation was the base of tracking, and learning the filter for correlation was the main idea in tracking, not deep learning. The correlation operation is a simple fusion manner to consider the similarity between the template and the search region. However, the correlation operation itself is a local linear matching process, leading to lose semantic information and fall into local optimum easily, which may be the bottleneck of designing high accuracy tracking algorithms. What these guys is asking is there any better feature fusion method than correlation? But transformer does this by attention. To address this issue, inspired by the transformer, this work presents a novel attention-based feature fusion network, which effectively combines the template and search region features solely using attention. Specifically, the proposed method includes an ego contest augment model based on self-attention and cross-feature augment model based on cross-attention. Okay, so let's go to that paper. Okay, so we're going to get there, don't worry. Yes, all the things that we already gone over. So as you can see, guys, this is their paper. What they do is they have so it is like a Siamese network, guys. This is the transformer version of a Siamese network. So I told you before sequence model based trackers, there were deep trackers, mainly Siamese networks, used the deep learning architecture to match template and the frames. They were not sequence modelers, but they were deep learning architectures used for training. This paper used the attention mechanism of the transformer to replace, or I don't know, to construct a similar architecture to the Siamese network. And you can see this from this entire architecture here. The template, the search region, fed to feature extractor, which is a ResNet 50, so pre-trained network. You have the template networks. So this is kind of an embedding, right? In the original vision transformer, the embeddings were learned by positional encoding because the sequence was important. But in this matching algorithm, the sequence is not important because this is a Siamese network manipulation, kind of manipulation. So we don't need positional encoding. That's why instead of using the embedding layer of the transformer, it is using a feature transformer from a classical convolutional network like ResNet50. These are template vectors. They are being fed to two models, ECA and FCA. This is the feature vision network inspired from the transformer. Then they fuse the vectors, and using regression and classification vectors, they kind of detect where this network is. So it is like, as you can see, they provide a very nice example. There's this plane, but in the template, the plane is taken from a different angle. So using high-level features and using attention, this guy can detect that this plane is actually this plane taken from another angle. So this part and this part is very similar to Siamese network idea, but in the heart of it, there's an attention-based mechanism, which they call the feature fusion network. They design a feature fusion network. Effectively, they use the features FZ and FX. SZ and FX are the output of the ResNet networks, these guys. Okay. They are being fed to this ECA, which is ECA stand for the ego context augment, which is actually the self-attention mechanism, guys, nothing else. Modules focus on the usual semantic context adaptively by multi-head self-attention. So it is like it's trying to find the relation between the features obtained from a frame, but it's their self-attention, their intra-relations. Okay, so this is the ECA. Nothing but multi-head attention, a residual connection, and then none. If you remember the transformer encoder, that's how the self-attention mechanism was operationalized. And the next one, the context fusion architecture, CFA, what they do is they combine the two attention mechanisms, just like the decoder of the transformer does, using a multi-head cross attention. These are multi-head, I mean, they are multiple heads. I think there was 4, yes, multiple head was 4. Yes. So they fuse the two information. The relations between where to focus on the image, which was the attention, is learned in these fusion vectors. And these fusion vectors are fed to some multi-layer perceptrons to learn the exact location. So don't be startled, the output is not an image, guys. The output is the location of the black box and the size of the black box. So this network just provides real values, not an image. So don't be mistaken. So that's how they apply the transformer attention idea for tracker like Siamese tracker. But as you can see, this is not, how can I put it, sequence model tracker. Although the transform is used, actually transformer's attention mechanism is used. It's not a sequence modeler. What nice, transformer tracking, they give it title. I wouldn't name it transformer tracking. Maybe they want it to be so simple that it would be the first thing that it comes to Google search when you type transformers and tracking. It's a perfect match, isn't it? However, there was another paper this June, which was a real sequence-to-sequence based transformer tracker, learning spatial temporal transformer for visual tracking. The title kind of explains itself. Before getting to that, any questions about the transformer using the attention for implementing a Siamese-like deep learning tracker? Any questions? I know you're tired. This will be the last paper. Okay, this paper is very nice, guys. Because when I first saw the vision transformer, I dreamt of doing this. I know that I didn't have the resources. I mean, the resources like computers and the students to do this, but I'm glad that somebody did it like in 6 months. Okay, so this is a new tracking architecture with an encoder-decoder transformer as the key component. So they use the actual transformer for tracking, just like a sequence-to-sequence modeler. The encoder models the global spatial temporal features dependencies in the input between the target object and the template, the search widget. While the decoder learns a query embedding to predict the spatial positions where the target is. So as you can see, we have the transformer. So this is the search region, this is the initial template. You fed them to a backbone. Backbone means a type of convolutional network to get the features again. They flatten and concatenate. As you can see, there is no positional encoding because just like the previous one, it is trying to find the relations between the two frames, the transformer encoder. And the transformer encoder's output is fed to the transformer decoder, and you're finding the next guy. So the transformer decoder is kind of doing the sequence to sequence stuff, just like the transformer does. Okay, so let me get to the paper. Yes, it is here. And since these guys know that they did something important, they kind of start with this nice graph. So where does Siamese RNNs hold? What is the speed of it, the success? And they say that it is here. So it is fast and it is very accurate. They're trying to say that you've got the best tracker. Okay, and if you're interested, you can just check these trackers. They've got a very nice comparison of different trackers. Okay, so with the encoder-decoder transformer, the prediction of objects just uses a simple fully convolutional network which estimates the corners of objects directly. The whole method is end-to-end, does not need any post-processing steps such as cosine window, bounding, like smoothing, thus largely simplifying existing tracking pipelines. Since transformers are quite highly parallelizable and they have high speeds as well. Okay, let's get to the thing. So let me go over this. I've got some annotations. So this is the search region. You feed this backbone to ResNet. It is ResNet. I've read it in the paper. They flatten and concatenate to feed it to the transformer encoder. All the self-attention, multi-head self-attention stuff is done here so that relations between these features and these features are learned in the self-attention. Because in the previous one, self-attention was applied to each one, the template and the search region separately, remember, in the previous transformer paper, CVPR paper, separately. But this guy do it in a combined manner so that this guy will learn the interrelations between the initial template and the search region. And it's being fed to the decoder. The decoder predicts a location. Again, do not be mistaken. The output of the prediction head is not an image, but this black box and its size. And the updated template is fed here. And the search region is always fed here. So just like a transformer. So this is the target query. It should be the target query. The target query is fed to the transformer. Actually, not this one. This is like the, yes, target query. There's a fully convolutional layer here as well. So it goes on like this. So the search region, the next search region will be fed here. The next template fed here, and it runs like this. Next search region, next template. They adopt a vanilla ResNet for the backbone. More concretely, except for removing the last stage of fully connected layers, there's no other change for the original ResNet. They provide a ResNet. And there's this box production heads, so bounding box prediction head, where the transformer outputs a value, and that value is used to create a heat map of the target. So it's like the decoder output, the encoder output, concatenated, multiplied, and there's a fully connected layer and multi-layer perceptron to create the heat map. And using that heat map, they obtain the outputs of the target. Always a heat map, the output is. Okay. And this is how they works a spatial temporal manner, the thing that I just drawn. So it is the dynamic template being fed. They somehow in their spatial temporal tracking, they keep the initial template as well, so that because if the dynamic template is, drifted, is lost, the initial template will always find its way through. So it's like the ground truth of it. But the dynamic template is to keep the recent changes in the appearance. So they have this. Okay. Links to these papers, and actually, if you cannot download them in OptoClass, I've got all of them with their annotations. Please go and download them. I think this pretty much provides a summary of how tracking can be applied to sequence models and how it can be treated as a sequence model. And if you're going to work on tracking, it's a very exciting problem because it's always state of the art. I strongly recommend you kind of get use of these approaches and try to implement them in your studies. And that's all I'm going to say, if you don't have any other questions. No? Okay. Okay then.